how to use the above described parameter applied to a real biological scenario. The study is called, has been performed with using a methodology called layered biological matrix. The study is the characterization of the radiosignal penetration in different kinds of biological tissues, and the environment under investigation is the parietal area of the human skull. The development model is based on propagation and absorption of electrical field in non-conductive materials. When an incident wave reaches the interface between two materials with different electromagnetic characteristics, its energy is partly reflected and partly transmitted to the following material. The biological tissue dielectric properties are strongly dependent on their structural properties like cellular architecture, presence of membrane, different response to electrical field by biological molecules, and so on. But all these properties affect the way the field's propagation in different ways at different frequency. In fact, at low frequency, the behavior of the tissues is strongly influenced by cellular architecture, while at frequency of the order of 100 megahertz and higher, the biological tissue reactions are simpler. They are influenced by dispersion properties of water and by the conductivity of the electrolyte is dissolved. The study has been organized into 4 steps. The first one is the characterization of the biological matrix. Step 2 is the definition of the layers. Step 3, numerical model implementation and identification of boundary conditions. The first step is the characterization of the biological matrix. The tissue present in the area of interest are 7. Stratum corneum, connective tissue, cranial bones with different morphology of the matrix, meninges, and in particular dura mater, cerebral cortex, the so-called gray matter, and deep brain, which is known as white matter. To evaluate the internal field in the following interface has been taken into consideration. The first is the path is from the air to the deep brain. The first layer is air stratum corneum, then stratum corneum connective tissue, corticular bone, cancellous bone, cancellous bone, corticular bone. These are 2 different type of bones. One is characterized by a high percentage of water inside, is the cancellous bone, and the other is characterized by a lower percentage of water inside. Then we got corticular bone, dura mater, cerebral cortex, deep brain. And what we must take into consideration is that the electromagnetic characteristic of each of these materials varies according to the frequency. Here we got the definition of the layers. Here are described the layers. I start from the last one because there is something to say about the first one. Here, the table on the left reports the thickness of the layers used to compute electrical field inside tissue. Values have been taken, of course, from medical literature, and they are related to a standard human male. The last layer, S7, represents the deep brain. Here we assume to consider the interface for the deep brain 2 centimeters below the cerebral cortex very inside the white matter composing the interior brain. The first layer has been calculated in a particular, have been treated in a particular way. Usually in numerical models, the stratum corneum is considered with a very small thickness, inferior than a millimeter. When we use in case of a multi-layer scenario, because the stratum corneum is composed by 3 different stratifications: stratum corneum, dermis, and fat. In this case, we set the stratum corneum to 1 millimeter. This is a derma-like approach. The stratum corneum has been supposed to be composed only of derma. We did not consider the skin stratification. This because our goal was not to characterize the skin, which have been studied a lot in literature, but is to characterize all what was below the skin, the other layers. Here we present finally the model. In this context, the electrical field propagation inside the human body for frequency from 26 to 100 gigahertz can be treated according to the geometrical optical rules at the interface between 2 different materials. The model is based on propagation and absorption of electrical field in non-conductive materials. When the electromagnetic wave reaches the interface between 2 layers, as a consequence between 2 different materials, its energy is partly reflected to the superior layer and partly transmitted to the following ones. The analysis has been performed considering a plane wave interaction, and before I told you that this approximation is valid when the size of the object interacting with the electromagnetic fields, like an organ or the interface between 2 organs, and in particular the relevant parameter is the curvature radius, is much greater than the wavelength of the incident fields. So this plane approximation is okay for field up to 6 from 6 gigahertz to the terahertz radiation, while at lower frequency the above condition is no more valid. If we want, is it possible to use again the geometrical optical rules at lower frequency? But analysis we performed show that this will result in errors of at least some percent for the computed internal field. Some percent can mean in some cases 20%, and this is not acceptable. An incident wave arriving to the body, striking the body, meets a different kind of tissues and various interfaces. The thickness of the layers varies according to the anatomical region and to the individual characteristic. The energy absorption is in different layers cause a decrease in the incident field energy. The model takes into account transmission and reflection, of course, first order of reflection. On the bottom of the slide, you can see the equation of the power, where Z for power and electric field, where Z is the distance traveled by the field in a given material, and delta is the penetration depth. The penetration depth with the formula I presented in the previous slide. Parameters. To perform the analysis, we use the following parameter. The parameters who should be known are the incident field power, which is known. We decided this value. The penetration depth that can be calculated. The reflection coefficient that can be calculated with the appropriate equations. The signal, the frequency of the radio signal is a known parameter, and the depth of the area under investigation, which is fixed from medical literature. The internal electric field is computed in an infinitesimal volume around the interface between two layers. In this case, the incident electric field has been set equal to 500 voltmeter. But if you want, you can change this value. We decided to use 500 voltmeter because this value of electric field is used for oncological hyperthermia, but it was just a decision, an assumption. The incidence angle has been set to 45 degrees, and this was also an assumption and was due to the fact that at 45 degrees, sin and cosine are equal, and this simplified the calculation. And the third assumption is that the interface for the deep brain is placed 2 centimeters inside the cerebral white matter. But also this parameter can be changed according to what you want to analyze. Here we present some results. On the x-axis, we have the layers. On the epsilon axis, we have the electric field in logarithmic scale. Here are presented also the thickness of the layers. This is the graph for 26 gigahertz. Here we got the graph for 40 gigahertz, for 70 gigahertz, and for 100 gigahertz. What is immediately clear is that all the graphs is that the absorption is different if we consider vertical polarization or horizontal polarization. This result, which at the beginning was quite strange for us, has been found in literature where other authors reach the same conclusion using different methodologies and different models. According to some authors, the difference in attenuation are due to different absorption by the body of the diffractive component as the polarization varies, and with different effective dimension of the area on which the waves strike. But this aspect has not been taken into consideration in this work. I mentioned this just because we found the same results in literature. From plots, it emerges that the confirmation that the absorption from tissues increases with the frequency. The absorption pattern is the same for each frequency, but what varies is the amount of electrical field that reach the deep brain. This amount of this electrical field reaching the deep brain is of the order of -11 and -14 according to the polarization for 26 gigahertz. Is of the order of 16, 18, -16, -18 for 40 gigahertz, and is the order of -24, -26 for 70 gigahertz and minus 30, minus 32 for 100 gigahertz. Here is we put all together the results to have an idea of how the frequency influence the absorption. Here are present the results of two spin-off studies. The first one was focused on the E-field level, if we change on the variation in E-field level inside the deep brain, if we change the deep brain position. And the other is related to the behavior of the stratum corneum. The first graph on the left shows the electric field within human brain as a function of depth, the parameter d in the equation for signal at 26 gigahertz and 100 gigahertz. The computation have been carried out with the methodology presented, starting from the field computed at the interface between cortex and white matter for values of the parameter t comprised from 0.5 to 3.5. If you ask me why I did not put the point for 3.5 is that the graph would be out of the slide. At just 0.5 centimeters of depth under the gray matter, the field at 26 gigahertz is 2 orders of magnitude lower than the one present at the interface between gray matter and white matter. The order of magnitude are more than 7, as many as 7 when the frequency is 100 gigahertz. The second spin-off study is related to the stratum corneum behavior. Skin and scalp are the primary interface between the biological components of the human body and the external environment. The scalp has been simulated as dry skin, whose characterization is well known in scientific literature. A numerical simulation carried out with the methodology showed that for an incident signal at 26 gigahertz, the electrical field decreases by 84% with respect to the original values. This percentage increasing the frequency. The last spin-off study I present is the attenuation as a function of water. The table, we chose 3 different tissues: cortical bone, stratum corneum, and cerebral cortex, having different percentage of water inside. We calculate using the described methodology, the econ 0, the electric field at the interface, the internal E, and then we calculate the attenuation. From the table emerges that tissue with low water contents causes smaller attenuation of electrical field than the one with higher water content. But such correlation is not a surprise, because an increase in the amount of water within tissue can cause an increase of the dielectric permittivity. With this slide ends the part related to the mechanism. And now I will present something related to effect of exposure. The electromagnetic fields is a physical agent and is one of the most studied agent. An assessment, very recent assessment of the effects of exposures to electromagnetic fields have been carried out at the end of 2023 by the SHEAR Committee. SHEAR Committees is European committees on emerging risk, environmental emerging risk. And this analysis has been carried out to the revision of the most recent scientific literature, publication from 2020 to 2023. Assessment that must be carried out in the form of meta-analysis, which means a combination of data from several similar studies to obtain a conclusion based on strong statistical power. The observed effects are, for the major part, thermal, due to overheating caused by the absorption of the energy by the tissue. And this is the reason why I split my talk into two parts. And the first one was focused on the absorption, on the study of the electromagnetic fields in biological tissue. For what concerns oncological pathology, the evidence that exposure to there is an evidence that the risk that exposure to radio frequency could cause cancer is uncertain or weak. The scale of values for this kind of analysis is uncertain, weak, moderate, or strong. So where the evidence has been found as uncertain or weak are the lowest levels of risk. No moderate or strong level of evidence has been identified in literature for any health effect associated with chronic or acute exposure to radiofrequency fields below the limits reported in the CNIRP guidelines, of course. Now I will explain, I will describe, but very, very fast because everyone knows this mechanism. What are the mechanisms of the thermal effects? Thermal effects of electromagnetic fields refers to material heating due to the absorption of energy from the electromagnetic fields. This is exactly what happens when we use a microwave oven. This phenomena depend on different factors: frequency and intensity of the electromagnetic fields. Higher frequency and higher fields generally lead to great absorption and heating. Properties of the material, the electrical conductivity and permittivity of a material determine how much energy is absorbed from an electromagnetic field. And exposure duration. Longer exposure time can result in greater temperature increase. Electromagnetic fields can cause polar molecules like water, but not only water, to rotate and vibrate to align with the oscillating field. This happens a lot of time in a second. And this molecular motion generates friction, leading to rising temperature. The molecules important and involved in this mechanism are water, and as we know, our body is composed for a big part of water. Carbohydrates, in particular, which are rich in hydroxyl groups, amino acid with the polar chains. All the amino acids, in fact, present an amino group and the carboxyl group that are polar. Nucleic acids, DNA, RNA, and all the nitrogenous bases, A, G, C, T, U, composing the DNA. Sugar phosphate, backbone of DNA and RNA, contains negative charges phosphate group and polar hydroxyl groups, so they can classify as polar molecules. What are the thermal effects? Thermoregulation is important. The human body has a present mechanism to dissipate heat, like, for example, increased blood flow and sweating. If the rate of heat absorption exceeds the body ability to regulate the temperature, it can lead to transitory effect, which disappear once the exposure is over. The heating can be localized, and this could be a problem because certain tissues like eyes and testes present limited blood flow, and for this reason are more susceptible to damage from localized heating. For example, a long-lasting hyperthermia in the eye region can contribute to cataract development. And pay attention because the cataract induced by hyperthermia is not reversible. The overheating of the testicles leads to a transitory decrease in sperm motility. This phenomena happens, but once the source of electromagnetic fields is no more active, the problem stops. Another problem is the whole body heating. Significant whole body exposure to electromagnetic field can raise the core body temperature, leading potentially to heat stress. A whole body exposure with a specific absorption rate of 4 vacuum kilo can cause a temperature rise of approximately 1 degree in humans. The specific absorption rate is a measure of the rate at which energy is absorbed by the body per unit mass. These values, which depend on the E-field level, is to the square of the E-field level, is used in ICNIRP guideline as a parameter to refer the limits, the exposure limits. And now we describe something about non-thermal effects. Non-thermal effects refer to a series of biological interactions that occur at energy levels too low to cause a significant increase in temperature. Non-thermal effects have been studied. Here I present the result of some of these studies, and they have been studies, but the results of this study are debated. The first non-thermal effect is gene expression and protein alteration. A number of in vitro on cellular culture and in vivo on animal study has suggested that the exposure to electromagnetic fields may induce changes in the expression of particular genes. The major part of these studies have focused on genes related to stress response, for example, the heat shock proteins, or related to cell cycle regulation, apoptosis, which is the programmed cell death, oxidative stress, and neurological function. But studies have been performed, but the results are often inconsistent and tend to depend of the specific parameter used for the study. For example, frequency, modulation, exposure, duration, sublevels, cell type, preparation of the cells. So the results are debated, and more studies are necessary. The second non-thermal effect is the oxidative stress. Oxidative stress occurs when there is an excessive production of reactive oxygen species, also known as free radical. These ROS are highly reactive molecules that can damage cellular components like DNA, protein, lipids, leading to cell dysfunctions and potentially contributing to various diseases. For example, cancer, neurovegetative disease, cardiovascular issues, and so on. Oxidative stress have been studied, but studies are often contradictory, and the relevance of this effect at low levels of exposures is still debated. Cell signaling. Some study in vitro on intra and intercellular signals reported that low radiofrequency level may interfere with communication pathway between cells. Mechanism can be of electric nature and can involve action potentials transmitted along the axons, electrical signals leading to muscle contraction, electrical potentials mediated by sodium and calcium, and a lot of effect, but the mechanism involved in this effect are not have not been defined in a clear way, and also biological consequences are not well defined. Some studies suggest that radiofrequency fields may alter the permeability of cell membranes. For example, there is a study that reports the induced leakage of albumin across the blood-brain barrier in rats due to the presence of electromagnetic fields. But this study presents methodological limitation, and all the attempts to repeat this study and to verify the results have failed. So this remains a no evidence effect. Intense pulse low frequency electric fields can cause a cell membrane to become permeable, allowing the exchange of intra and extracellular materials. This effect is known and is called electroporation. Some study refers that exposure to unmodulated 18 gigahertz field create a similar effect, but this study has been performed using very high field strengths, so the effect cannot be considered. Cognitive function. Some studies report that electromagnetic field exposure can have an impact on cognitive function, such as memory, attention, and reaction time. But most double-blind human experimental study on cognitive performance did not report an association with radiofrequency exposure. There are a great number of sporadic findings, but the results don't follow a meaningful and consistent pattern. Maybe those results are due to a large number of statistical comparison and maybe occasional findings. Some decrease in memory performance in rodent and in non-human primates have been detected for SARS over 5 watt on kilos. If you remember, a star of 4 watt on kilo is able to produce a whole body temperature decrease of 1 degree. Researchers in this case are agreed that the effect of a decrease in memory performance could be due to the core body temperature increased by more than 1 degree. Some people report sleep disturbances in relation to radiofrequency exposure. In this case, scientists have not established a clear causal link. There is a known effect on 10 gigahertz frequency range produced by brain, waves produced by brain during the sleep, which are affected by the exposure to radiofrequency field. But this happens for stars inferior to 2 watt kilos, but there is no evidence of adverse effect. All these efforts, in any case, are still under investigation. Research has a lot of work to do to complete the framework of effects. And here, the part creating master worries. It's cancer. Cancer has been studied through epidemiological study, in vitro study, and in vivo on animal study. Epidemiological study have been performed using cohort study or other kind of studies. And to have a complete knowledge of this kind of potential effect, all the 3 kinds of study are necessary. There is a large body of literature concerning cellular and molecular processes that are with particular relevance to cancer. The studies include the cell proliferation, differentiation, apoptosis-related process, proton cogen expression, genotoxicity, increased oxidative stress, and DNA trans break. Some reports can be positive for some of these endpoints, but there is no substantial evidence that of health-related effect. Some animal studies on the effect of radiofrequency electromagnetic field on cancerogenesis reported positive effect, but in general, the study have shortcomings in methodology or in dosimetry, or the results have not been verified in other studies. In addition, the study for what concerns cancers, the study related to animals are very difficult to be applied as a total to human, because for cancer, human and animals follow different metabolic pathways. A large number of epidemiological studies, as I told before, on mobile phone use and cancer risk have also been performed. Most have focused on brain tumors, in particular acoustic neuroma, parotid gland tumors, because those parts are in close proximity to the phone, which is the typical exposure. But some study on other cancers have also been performed, like, for example, leukemia. Leukemia has been intensively studied because unfortunately there is an association between low frequency fields and some kind of leukemia, or studies have been performed on lymphoma, uveal melanoma, pituitary gland tumor, testicular cancer, and also on malignant melanoma. With a few exceptions, the study have used case control designs, and in general, they rely on retrospective collective self-reporting information about mobile phone user history. The self-reported information is not a good marker for dosimetry, because it's not possible to, from self-reporting information, to define a real number representing the dosimetry. And in addition, the distortion of the remembering, of the memory, tend to increase the number of hours spent at the phone by the patients. Only 2 cohort studies with prospective exposure information are available. In addition, several studies have had follow-up too short, and so it was not possible to see a real long-term exposure. And in some other studies, follow-up were not consistent. The large interphone study, the one coordinated by the YARC, did not provide evidence of a raised risk of brain tumors, acoustic neuroma, or parotid gland tumors among regular mobile phone use. And the risk estimates did not increase with longer time since the first mobile phone has been used. In addition, no cohort studies report higher risk of glioma, meningioma, or acoustic neuroma among mobile phone subscribers. The large prospective studies, Cosmos, have not shown a significant increase in the risk of brain tumors or other types of cancer associated with cell phone use or exposure to environmental radiofrequency fields. In any case, all the efforts related to cancer are still under investigation. The research activity continues, a new priority has been identified. The research priority is really important, and in the last year has been identified by World Health Organization and by SHEAR at the European level. World Health Organization in 2024 has commissioned a systematic review of the epidemiological and experimental evidence focalized on 6 effects and mechanisms: heat-related effects, cancer, fertility, cognitive function, symptoms, and oxidative stress. The analysis and synthesis of this evidence is still ongoing, but results will be published maybe this year in a monograph of the Environment Criterial Health Series. The systematic reviews carried out by World Health Organization on the available literature concern a list of outcomes. For this list, I will thank you, Serena Fiocchi from CNR, who have given me all the information about this list. The considered outcomes are heat-related illnesses, cataract, pain, and burns in humans and animal studies, cancer in human observational studies, cancer in experimental animals, fertility and pregnancy outcomes in human observational studies, fertility and birth outcomes in experimental animals, cognitive function in human observational studies, symptoms in human observational studies, symptoms in human experimental studies, and oxidative stress in experimental animal and cell studies. Scherer identified different priority. In late 2022, Scherer proposed a public consultation on the need for a technical revision of the annexes to the Council Recommendation 1/1999/419 and Directive 2014-35 related to exposures for general public and workers. Scherer decided to launch this public consultation because was aware that technology advances and emerging wireless application, in particular the use of new frequency in the millimeter wave spectrum, require the introduction of limits for new dosimetric quantities. 240 contributions come in response to the consultation, and all have been taken into consideration. At the end, the priority defined by Scherer are the development of a number of World Health Organization protocols for systematic review in order to strengthen the level of evidence about health effect. They wanted to introduce a common protocol both for the research and also for the analysis and the review. More research in the higher frequency bands, in particular in the millimeter wave. This is because the research, a great amount of research has been done, but most of this research is focused on legacy frequencies. Some research is present on 2.1, 2.6 gigahertz, 3.5 gigahertz, but the literature, there is little literature on 6 gigahertz, 26 gigahertz, 40 gigahertz. So it's necessary to investigate on these frequencies. It's necessary to investigate on the interaction mechanism of radio frequency electromagnetic fields and to study effects different from the thermal ones. And then it's necessary, according to Scherer, to improve methodological quality criteria about experimental design, exposure control and assessment, in particular dosimetry, and statistic results and analysis. For what concerns symptoms, it's necessary before symptoms are not related to exposures or symptoms are related to exposures, it's necessary to include objective measurements of physical, biochemical, and biological markers in response to exposures. Here I describe some restart activity. I will go quickly on this part related to the argument I present. In particular, spoke 3, work package 1, task 1.3 and task 1.3.1, which related to in vitro biological investigation, and task 1.3.2 is the task I'm working for, in electromagnetic coverage and exposure assessment to computational technique using analytical and numerical methods and innovative strategy to combine stochastic and machine learning. At the moment, we have performed a comparison among the simulation tools to test the reliability in the evaluation of electromagnetic fields, experimental validation with measurement at 3.7 and 26 gigahertz. We identified the optimal theoretical model for evaluating electromagnetic field coverage. We describe a systematic method to compare different ray tracing tools And this method has been applied to the evaluation of 3 different tools, a commercial one and 2 proprietary tools, and prediction has also been validated using measurement at 3.7 gigahertz. In addition, we perform a ray tracing study on a real case hospital scenario to consider the development of a class A2 low power 5G non-public network operating at 26 gigahertz. This work is being consolidated into a paper submitted and accepted for the BioM 2025 conference. And we study also spatial power monitoring in massive MIMO technology. Other topics regard the phantom design for dosimetry assessment up to 60 gigahertz, computation assessment of human exposure in V2V communication scenario, and computation assessment of human exposure in indoor scenarios, including reconfigurable intelligent surfaces. Now we are at the end of our talk. I present you 2 slides, who are the information I would like you to remember and to take at home with you. When a high frequency radio signal interacts with a human body, its outermost interface, skin, scalp, absorbs a considerable fraction of the incident power, and this can lead to local heating, which can have effect. The fraction of absorbed energy increases with the frequency. Signal polarization affects absorption by tissue, which is higher for signal with vertical polarization than for the one with horizontal polarization. Tissue containing a relatively low water percentage attenuate the radio signal much less than those with higher water contents. The percentage of power reaching the deepest and most delicate parts of the body, like brain, internal organs, liver, is to be considered negligible for high-frequency radio signal up to 500 watt-meters. And all these findings must be considered while describing the effects of high-frequency electromagnetic fields. What are the conclusions on effects? The effects of exposure to electromagnetic fields have been extensively studied by the scientific community from the end of the Second World War. Electromagnetic fields are one of the most studied physical agents. The known biological effects are mostly of thermal nature. Non-thermal effects refer to a series of biological interactions that occur at energy levels too low to cause a significant increase in temperature. These effects are present. They have been seen in some experiments, but are still debated. A study has not shown a significant increase in the risk of brain tumors or other types of cancer associated with cellular phone use or exposure to environmental radio frequency fields. Of course, I speak of radio frequency fields below the ICNIRP's guideline limits. Some studies reported weak or inconsistent association, but most of the studies present methodological limitation, in particular for what concerns the dosimetry. Of course, new research priorities have been identified, and the research go on. Thank you for your attention.